Okay, so these notes are going to be over just gas collection. So just take these notes. There aren't any questions that go with them. But just take the notes, and you're still responsible, of course, for the material. Kind of has to do with the lab that we did in class last time, where we collected the gas from the air duster and tried to determine its molar mass. So there's one source of error inherent in that lab that we didn't talk about prior to the lab. It doesn't make a huge difference in your answer, but it does need to be considered for future experiments where we're collecting a gas by water displacement. So if you haven't taken these notes already, go ahead and pause and take them. You want to draw at least a rough picture of the apparatus you see there in the picture, and then I'll explain. Okay, so when we look at what's happening here, there's a reaction happening inside of this test tube. It looks like we're just breaking down some potassium chlorate, and the gas, oxygen, being one of the products of that decomposition, would just go through this tubing underwater and into this bottle. And it's being collected right here, and we would find the volume of the gas sample. We would look at the pressure in the room, assuming it's about the same as the pressure inside the bottle. We look at the temperature of the room, again assuming that it's about the same as the temperature inside the bottle. And we look, of course, at the volume of the gas, and we should be able to figure out how many moles of gas we have. And so that allows us to, to measure a gas sample, even though we can't put it on the scale to get an actual yield. We can see if we got our, close to our correct yield of that oxygen by doing the reaction. So as I said, there's an inherent problem with using PV equals nRT, and the problem is this. Whenever we collect the gas by water displacement, there's always some water here at the bottom of our sample that is going to be evaporating. And so that means that some of the gas inside of this bottle, inside of our sample that we're calling oxygen, some of that gas is actually water vapor, okay? So the only thing that really affects in PV equals nRT is it affects our pressure. The temperature obviously doesn't change just because there's some water vapor in there. The volume doesn't change because all gases occupy the same volume. So it is fair when we're doing PV equals nRT. It is fair to say that, the volume that we plug into the equation is the volume of oxygen. We can say that the temperature is the temperature of the oxygen. Okay, but the pressure is actually created by both oxygen and water vapor, the water that has evaporated inside our sample. Okay, so there's a mixture of gases. Now, it's not going to be a huge amount of pressure created by that water vapor, but it can, at certain temperatures, really affect, or affect slightly at least, our number of moles that we calculate. And so the idea that all of the pressures in a mixture of gases add up to a total pressure is called Dalton's law of partial pressures. So the same, Dalton's atomic theory, Dalton's law of partial pressures says that the total pressure in the sample is going to be equal to the pressure due to each individual gas. So if I'm talking about the total pressure in the room, and let's say the pressure is, we'll just use mmHg. Let's say the pressure is 760 mmHg. Well, that's going to be equal to the pressure due to nitrogen, which is going to be a big number because nitrogen makes up most of the gas in the room. Let's say it's, 600 mmHg, plus oxygen, which is going to make up another, 150 mmHg. And then, other gases like, CO2 and water vapor, et cetera, et cetera, et cetera. So, we just keep adding those values up, And together, they equal our total pressure 760. So that's the idea. So how do we know how much water vapor is in our sample? Because if I'm going to solve for my number of moles of oxygen, if I want to know my number of moles of oxygen, I'm going to rearrange PV equals nRT to say, PV over RT equals N. But I want to make sure that all of these values, pressure, volume, and temperature are all for the oxygen only. And as I said earlier, the volume and the temperature, that's not a problem. We can say that whatever the volume is the volume of the oxygen. We can say that whatever the temperature is the temperature of the oxygen. The pressure, though, we have to subtract the pressure due to the evaporated H2O, because that is making up some of the pressure in the sample. So how do we know how much to subtract? Well, it depends on temperature, because the warmer the water is, the more evaporation you'll have, and the higher the pressure due to water vapor is going to be. So you're given a table, and this was actually on the backside of the Ideal Gas Law worksheet, so you have a copy of this. But this is called just water vapor pressure, or partial pressure, sometimes we call it, due to water vapor. And at a given temperature, the pressure will, due to water vapor, will vary. So if we're at the freezing point, there's going to be very, very little pressure, whether we're in MMHG or KPA, because there's not going to be a lot of evaporated water because we're right at the freezing point. If we go all the way up to the boiling point, the pressure is going to be standard. Essentially, it's going to be atmospheric pressure. That's why the water boils, because the pressure due to evaporating water has become so great that it actually equals the pressure from the atmosphere, and so we have rapid evaporation, otherwise known as boiling. Most of our experiments are going to be done in this range, from about 20 to 25 degrees Celsius, and so we're going to have, maybe 17 to, 24, 25 mmHg, and then you could see the corresponding values for kPa as well, that we're going to have to consider subtracting from our total pressure if we want to know the if we want to know the true pressure due to the gas we're trying to collect. Okay, so if all this is a little confusing, let's do an example problem. Let's say we're collecting oxygen, and let's say how many moles of O2 would we have collected if it occupies 45 milliliters at 765 mmHg and let's say 25.0 degrees Celsius, and we're assuming that this is being collected by water displacement or collected over water. Okay, so we'll set up our equation. We'll rearrange PV equals nRT to get N equals PV over RT, and we're going to be able to plug in some stuff, but not everything. If we're in mmHg, our R value is going to be 62.4. Our temperature, 25 degrees Celsius. If I add 273 to that, I get 298. Our volume is going to be in liters so that it matches the unit in the R value. So 0.045, right? Yeah, 45 milliliters. Okay, and then the pressure, all we have to do is take the total pressure, 765 mmHg, and subtract the partial pressure due to evaporated water at that temperature. So we just find our temperature on our chart, 25 degrees Celsius, and it looks like at 25 degrees Celsius, the pressure due to water vapor would be 23.8 mmHg. So I'm going to subtract 23.8 mmHg. And let me go ahead and get out the calculator. Okay, so it looks like I get 0.001794, which looks like I only need 2 sig figs because of the volume being 2 sig figs. So 0.0018 moles of O2. So you can see there that, you know, depending on the temperature, 23.8 being subtracted from 765, it's probably not going to change your answer a whole lot because it's a relatively small percentage of the total pressure. But it might change it a little bit. And the warmer the water is, you know, the higher you go in the scale, you know, if you have 35 degree Celsius water, then, you know, that number becomes a little bit more significant, and it does need to be considered. So from now on, whenever you see on an ideal gas law problem that a gas is collected by water displacement or collected over water, then we need to subtract the number from the table.